Bismillahirrahmanirrahim. Hello everyone. This is the sixth part. We will solve the linear Volterra integral equation this time using the successive approximations method, or we can call it Picard iteration method. This is our fifth method. Let's see how can we use it to solve the linear Volterra integral equation. Here are the steps of the successive approximation method. The first step, you guess or put an initial value for u0 of x, and then you use the recurrence relation of the method, which is un of x equal to f of x plus lambda, the integration from 0 to x, k of x in t, un minus 1 of t dt, where n is greater than or equal to 1, okay? As we can see, it's the form of the linear Volterra integral equation that we are trying to solve. If I put n equal to 1, then I will get u1 by the value of u0. And if I put n equal to, then I will need u1 to get u2, and so on. In the end, I'll get the value of u of x, which is the solution, and this is by getting the value of un plus 1 of x, and then take the limit of un plus 1 of x, where n approaches infinity, and this is our solution. As always, these are the examples. The first group we will solve it together, and the second group you will do it yourself, okay? I want to talk about u0 of x, okay? Commonly, we put u0 of x equal to 0, 1, or x. Does that affect the answer? No, it just affects the speed of obtaining the answer. Maybe if you choose u0 equal 1, you will be slower to obtain your answer, comparing to if you choose u0 equal to x, maybe. But in general, the safest way is to put u0 equal to 0. Okay, so the safest way is to put u0 equal to 0. This is the first question. As we can see, it's not Volterra, it's Fredholm, but it's fine. We will solve it with the same steps, okay? The first step is put a value for a u0, for the u0. So u0 will be equal to 0, okay? Let's take the safest initial value. Our recurrence relation will be as the following: un of x equal to 1 plus the integration from 0 to 1. That's why we said it's Fredholm. Okay. X un minus 1 t dt, where n is greater than or equal to 1. When n is equal to 1, u1 of x will be equal to 1 plus the integration from 0 to 1 x u1 minus 1 naught of t dt. u0 is equal to 0, so this is all will be equal to 0, and u1 will be equal to 1. When n equal to, we have u2 of x equal to 1 plus the integration from 0 to 1. Remember to substitute in the recurrence relation. X u n is equal to 2, so 2 minus 1 is 1, t dt. u1 of t is equal to 1, so 1 plus x, integration from 0 to 1 dt, and that will be equal to 1 plus x t from 0 to 1 is 1. Okay, so 1 plus x. Then at n equal 3, u3 of x will be equal to 1 plus the integration from 0 to x u n minus 1, which is 2, of t dt. And that's equal to 1 plus x. Again, the x will be out of the integration from 0 to 1. From 0 to 1, not from 0 to x, sorry. Okay. u2, which is 1 plus t dt, and that will give us 1 plus x t plus t squared over 2, and that's from 0 to 1. And this will give us exactly 1 plus x, 1 plus half. Okay? Let's keep it this way, okay? Let's keep it as 1 plus half. Okay, let's complete by getting n when we will get u4 at n equal 4, 1 plus the integration from 0 to 1 x multiplied by un minus 1, which is 3 t dt, and this will give us 1 plus x again outside the integration from 0 to 1, 1 plus x, 1 plus half, okay, dt. Of course, this x should be equal to t, not x, okay? We should represent u3 of x as u3 of t here. Okay, that's why we exchange this x, okay, and write it as the parameter t. And this will be equal to 1 plus x. Let's integrate. That will give us t plus t squared over 2. 1 plus half will remain the same, and that's all from 0 to 1. And that will give us 1 plus x multiplied by 1 plus 1 over 2 disturbed is 1 over 2, so we will have 1 over 2 plus 1 over 2 squared. Okay, so we can now imagine how it will grow our un. Okay, in the beginning it was 0, and then it began to grow and become 1, and then it become 1 plus x, as if here we have 1. Okay, and then next to the 1 we add half, and then after we added half we added 1 over 2 squared. So we can imagine how it will look like. So it will be like this. When n equal n plus 1, what will happen? Un plus 1 will be equal to 1 plus x, 1 plus half, plus 1 over 2 squared, plus and so on till 1 over 2 raised to what? It was here raised to 2 when it's 4, so n minus 2. Okay, so it will be n minus 2. That's it. Now to write our u of x, in the board. So when you write un plus 1, you don't write the last one 1 over 2 n minus 2, as I said before. You write 2n plus 1 and then minus 2, because the term here is n plus 1, not n. Okay, so what we get here, we get 1 plus x multiplied by 1 plus half plus 1 over 2 raised to 2, plus and so on, plus 1 over 2 n minus 1. Okay, what do we call this? We call it a finite sequence. Okay, and we need its sum, and its sum is as the following: Sn is equal to a multiplied by 1 minus r raised to n over 1 minus r. Okay, what is a? A is the first term, which is 1, and what is r? R is the base. Okay, when we say half over 1, it will give us half, and then 1 over 4 over half will give us half, and so on. It's as if we are saying an plus 1 over an. If these are a naught, a1, a2, and so on, and that will give us 1 over 2. Okay, so what we will write here is 1 minus 1 over 2 raised to n over 1 minus half. Okay, and this will give us half. Here in the demonstrator we will get half, so 2 will go up, and then this will be multiplied by 1 minus 1 over 2 raised to n. Okay, so we can write this here down. 1 plus x, and there is 2 here, so 2x, 1 minus 1 over 2 raised to n. Okay, now we will take the limit for both sides when n approaches infinity to get the ux. So ux will be equal to limit n approaches infinity for un plus 1 of x. And this will give us 1 plus 2x multiplied by 1 minus 1 over limit n approaches infinity for 2 raised to n. Okay, and this will give us what this part is, as if we are saying 1 over infinity, which is 0. So this will give us 1 plus 2x. Okay, and this is our u of x. Okay, this is the second example. Here we will use again the successive approximation method, but as you can see, this equation is not Fredholm, is not Volterra integral equation, it's Fredholm integral equation. How do I know this? Because the limits of the integration are what are constants. One of them is 0 and the other is pi over 2. Okay, so now we will go with the same steps. The first step is that we write un of x is equal to the summation n from 0 to infinity u of x, okay, sorry, equal to un of x. Okay, and then we put u naught of x with 0 or 1 or x. I tried with 0, it was hard to guess the un plus 1, so let's pick u1. Try it with 0 and see if you can do it or not. Okay, but we will pick the easy one, which we will guess that we will put u naught of x equal to 1. And to get the rest, we write the recurrence relation, which is uj of x equal to sine x plus the integration from 0 to pi over 2 sine x cosine t u of t with an index which is j minus 1 dt. Okay, where j is greater than or equal to 1. Let's write u1 of x, and this will give us sine x plus, we can put sine x outside the integration because the integration is with respect to t, so it will not affect sine x. Okay, the integration from 0 to pi over 2 cosine t u naught of t. What's our u naught of t? Is 1. Okay, so our u naught of t is 1. What's the integration of cosine t? The integration of cosine t is sine t. Okay, so we can write sine x plus sine x. The answer is sine t from 0 to pi over 2 for this integration, of course. And this will give us, again, we write sine x plus sine x and substitute with the limits. So we get sine pi over 2 minus sine 0. Okay, when we draw it, the sign at 0 is equal to 0, and at pi over 2 it will be equal to 1. Okay, and this will give us exactly 2 sine x. Okay, let's get u2 of x. Okay, u2 of x, it will give us sine x. Always look at here and substitute, plus sine x outside the integration, and the integration from 0 to pi over 2 cosine t u1 of t dt. Okay, and this will give us sine x plus sine x, the integration from 0 to pi over 2 cosine t. What is our u1 of t? It's 2 sine t, 2 sine t, okay, dt. Of course, the 2 can be out of the integration, and we have sine t, cosine t. What's the integration of cosine t, sine t? As you can see here, we know that d sine t over dt, or d over dt for sine t, is equal to cosine t. So if we rewrite this integration, it will be sine t d sine t over dt, of course. And this will give us, according to the integrations rule, sine t squared over 2 plus c. Okay, so what we can write here is sine x plus 2 outside this 2, okay, sine x multiplied by the answer, which is sine t squared over 2, and this is from 0 to pi over 2. We don't write plus c, of course, because this integration has limits. Okay, and this will be equal to sine x plus this 2 will go this 2, and this will give us sine x sine pi over 2 squared. Sorry, there's a problem, but keep up with me. Sine 0 squared. Okay, so we have sine pi over 2 squared, which is 1, and sine 0 squared, which is 0, and this will give us what? This will give us 1. Okay, so we will get 2 sine x. So the final answer here will be 2 sine x. Okay, if you get u3 of x also, it will give us 2 sine x. So when we write un plus 1 of x, it will be nothing but what? If you can see here, we have u0 is 1, u1 is 2 sine x, u2 is 2 sine x, u3 is 2 sine x. So we guess that un plus 1 of x is equal to 2 sine x, because it's not changing and it's not growing in a certain way. It's just giving you the same answer all the time, over and over again. So if we take the limit of n plus 1 of x, where n is approaching the infinity, we will get that u of x is equal to 2 sine x, okay? And you can check that out by Mathematica and you will find that it is right. I hope so.